Let's consider what the conditions of equilibrium can tell us in terms of defining and understanding a physical situation. In this case, we have a person who is leaning against a wall with a basketball to provide some support to his back. Let's use the equilibrium conditions to explore two questions. First, what loads are acting on the player and his ball? And second, what is the relationship between these loads? To answer the first question, we need to draw a free body diagram. Before we draw the free body diagram, we need to define the system. We identify the player and the ball as a system and isolate it from the surroundings. To isolate it, we draw a line around the player, between the wall and the ball, and then between the soles of his shoes and the pavement, and then we remove everything outside the line. When we draw the free body diagram, we need to consider the forces acting on the boundary of the system. For convenience, let's put some labels on this free body. Call the place where the ball touches the wall point A, and the place where his feet touch the ground point B. To complete the free body diagram, let's start by adding the force of the wall pushing on the ball at A. We are assuming the wall is fairly smooth and provides negligible friction force. Then we add the force of the ground pushing up on his feet at B. We also need to add the friction of the floor acting on the feet at B. Here I'm going to use my intuition to guess whether the friction force acts to the right or left. Since if I were to try this, I would expect my feet to try to slide to the right. I think the friction force is acting to the left to keep everything stationary. The analysis will tell us if this guess is correct. Finally, we add the weight of the system, which consists of the player and ball. We place it at the center of mass of the system. To complete the free body diagram, I'm going to add some dimensions. I've added the distance between the ground and the normal force at A, and I've added the distance between the two vertical forces. So this answers the first question about which forces are acting on the system. To answer the second question about the relationship between these loads, we will use the conditions of equilibrium. The first equilibrium condition tells us that all the forces must add to zero if the system is in equilibrium. Let's start by looking at the horizontal forces. The force at A and the friction force at B are the only two horizontal forces acting on this system. Equilibrium requires that the rightward normal force of the wall acting on the ball be balanced by the leftward friction force. In other words, these two forces are equal and opposite. If they weren't balanced, the system would move in the horizontal direction. A similar situation occurs with the two vertical forces, which are the weight of the ball player's system acting down and the normal force acting upward at B. The equilibrium condition says the weight of the player and ball must be equal and opposite to the normal force of the ground acting at the player's feet. If they weren't equal, the system would move in the vertical direction. The system has two couples acting on it. The first is a couple created by the two horizontal forces separated by distance h. This couple causes a clockwise moment. The second couple, shown here in blue, is created by the two vertical forces separated by the distance L. This causes a counterclockwise moment. The equilibrium condition states that the sum of all moments acting on the system must be zero. In other words, the clockwise moment must balance the counterclockwise moment. This tells us that F sub A times H must equal W times L. If the moments don't sum to zero, rotation will occur. In summary, the equilibrium condition tells us that the horizontal forces must be equal and opposite, that the vertical forces must be equal and opposite, and that the two couples must be equal and opposite.